Buffers are solutions that resist changes in pH. They consist of a weak acid or base and its conjugate in the form of a salt. For example, acetic acid is a weak acid. Its conjugate base is acetate, and together they form an equilibrium system called a buffer. There are two ways to make a buffer. The first is to just add the weak acid or base and its conjugate salt together. So we can combine acetic acid with its conjugate base acetate in the form of a salt, so sodium acetate. The second way to make a buffer is to add a lot of the weak acid or base and just a little bit of strong acid or base to go with it. So if we add a lot of acetic acid and just a little bit of NaOH, a partial neutralization reaction will occur. Some of the acetic acid will be used up, and some of it will be left over in the beaker, but all of the NaOH will be used up. The reaction will form some of the conjugate salt. So what's left in the beaker is just the weak acid and its conjugate base in the form of a salt, which is a buffer. So how do buffers actually work? What happens when you add a strong acid or base to them, and why doesn't the pH change? Let's start with a strong acid. If you add HCl to our acetic acid and sodium acetate buffer, the sodium acetate and HCl will dissociate into its ions. The sodium and chlorine ions are spectators, so we can cross them out. And we're left with H3O+ in our beaker. Normally, the H3O+ would make the solution more acidic, but the H3O+ in a buffer will react with the conjugate base to form more acetic acid and water. So even though H3O+ normally changes the pH, it doesn't because it's converted to water, so the pH remains constant. Now if we add a strong base to our buffer, like NaOH, the sodium acetate and sodium hydroxide will dissociate into its ions. The sodium ions are spectators, so we can cross them out. And we're left with OH- in our solution. Normally, OH- would make the solution more basic, but the OH- in a buffer will react with the weak acid to form more conjugate base and water. So even though OH- normally changes the pH, it doesn't because it's converted to water, so the pH remains constant. Because buffers are an equilibrium system, we can use an icebox to determine their pH. The example gives us NH4+ for the weak acid and NH3 for its conjugate base. Write out an equation for the buffer, which is the weak acid reacting with water to form its conjugate base. When you fill out the icebox, remember that there's an initial amount of the weak acid and the conjugate base, because we're starting out with both. Cross out the water because it's a liquid, use X in the change column, and K is small, so X will be negligible for the acid and base because we're already starting out with an initial amount. Now use the equilibrium expression to solve for X. The solution is acidic, so you can use Ka in the equation. Then use the concentration of H3O+ to solve for the pH. The pH comes out to 9.7. We can actually use the Henderson-Hasselbalch equation to calculate the pH of a buffer. It's exactly the same as using an icebox, so let's try it with the example and see if we get the same answer. First, use the given Ka to calculate pKa. Then use the pKa and the concentrations of the base over the acid to calculate the pH. The pH comes out to 9.7. The Henderson-Hasselbalch equation is on your equation sheet, so you don't need to memorize it.